Welcome to the Global Connection, a Tel Aviv University podcast. Journey with us as we discover how TAU's academic community and friends are engaging with and helping to shape this ever-changing world. Hi, everyone. Welcome to the Global Connection. I am happy to welcome Dr. Eyal Ben-Dor, a professor in the Department of Geophysics here at Tel Aviv University, whose research focuses on soil spectroscopy, which is where you take a specialized device like a spectrometer to analyze the spectrum of light emitted from a small sample or object to determine its makeup. Professor Ben-Dor also focuses on hyperspectral remote sensing of the Earth, which involves capturing spectral information from a large area, usually through an airborne or a satellite-based sensor. Ben-Dor is head of the Remote Sensing Laboratory at Tel Aviv University, the leading group in Israel for imaging spectroscopy. And I wanted to have him here today as he's working on a new international project related to the remote sensing of the Earth in collaboration with a number of space agencies, including NASA, the European Space Agency, the Israel Space Agency, and more. So welcome, Professor Ben-Dor. Thank you for joining me.
Thank you. I'm very happy to be here and will welcome questions, and also will be happy to elaborate more on this technology.
Okay, great. Well, I may begin with the elaboration because I gave a bit of a definition of my understanding of hyperspectral remote sensing, but I have a feeling you know more about it, much more about it. So I'm wondering if we could start there and you could let the listeners know what it is.
Yes, hyperspectral remote sensing is actually an ancient technology. I mean, only recently people are aware about this technology, but it evolves 35 years ago in NASA JPL. And this is a way to get images that you capture with more than, let's say, 100 colors.
Okay.
And those colors are actually above the sight of light, and it is for the first time you get a pixel in the image that has not one wavelength, one information. So it's not a grayscale, it's not RGB, which has three colors that you have the brain and sense of sight to look at it, but it is more than samples and channels that you don't see by your naked eyes. And having this together in one image is hyperspectral remote sensing. So if you have a pixel with many, many bands, you get a spectrum. And a spectrum can be analyzed differently as we analyze the object in our naked eyes and with our brain. And you can get all kind of mathematical analysis to this data and get information from the data that you didn't expect. And this is actually happened for the remote sensing, as I said, in JPL. But today, this technology is also used in the laboratory for many, many disciplines: medicine, food science, civil engineering. So it's not actually isolated technology for remote sensing. It's also for close sensing. And today you can see information not in 3 dimensions, but in 200, 500, and maybe 1,000 dimensions, which is spectral dimensions.
Okay. I've heard a comparison, like if we were in the medical field, it's like going from X-ray to MRI. So really that just the amount of data and information that you're able to get from hyperspectral remote sensing, it's a whole other level. So can you talk about the significance of that breakthrough a bit of, moving from 2D to, like you mentioned, did you say 1,000D even, or, many, many more levels of information?
Exactly. I think the medicine discipline is a very good example because we started many years ago with X-ray. And in X-ray, you see only maybe the bones, and you see only one object in the body. And then we move to MRI, that you see more. CT, you see more, and MRI, you see even more. So in the remote sensing, we started with grayscale images. It's a photograph with black and white photographs. So we see objects, but we don't know the object what they are, because we can determine the object by the structure, but not with the chemistry and physics of the structure. So we went more than that, and we are now having three bands, three channels that provide us color. So this is going from X-ray to, let's say, CT. This color shows you more information about the object. So it's a water, it's a soil, and perhaps it's a building that painted black or painted blue, but this is not the entire information. And then we move to MRI, which is more than 200 colors that provide you spectrum. And this spectrum can give you information that you didn't pick up with the grayscale, with the black and white, and with the color images. And this information can be then analyzed chemistry and physically, and you can get information that you didn't expect.
Okay. Okay. So it sounds like before, you would have a certain amount of information and you would know sort of the trends and patterns to pick up on, and that could tell you a certain amount of information. But now that's been blown wide open in terms of the precision of the image. So it's a lot easier to detect. But not only that, it's all of the information you can get and what you can do with that. So you gave some examples before that this is helpful for a lot of different fields like food sciences. What can you talk a little bit more about that, about the applications, about what you can do with this technology?
Yes, it's very interesting, your question, because I started with remote sensing, and then I found out that this technology can work with other disciplines. And I work in these disciplines in medicine about 10 years ago. And we were trying to find out inflammation in the skin of the body and what is causing to this inflammation. And then I moved to civil engineering. In civil engineering, I was able to determine the strength of concrete by this technology without any damage to the wall. And then we moved on to asphalt, friction coefficient of asphalt, that is very important in terms of paving the road, or maybe even to prevent accident. If you have oil spill on the asphalt, or you have water spill on the asphalt, you don't know. It's the same for your naked eyes, but the technology can depict this information on the drive, can provide you hazardous information that you will be care of. And also, we were using this for clothes, for textile, to find out what is the textile composition. And of course, then we move to what we call agriculture.
Okay.
In agriculture, it's a very much information for the vegetation, for the soil, for the water, and this opened a very wide range of applications.
Okay. Okay. Which brings me a little bit to the current international project you're working on with space agencies. It sounds like so there is a big application here um, when working with space agencies in terms of remote sensing of the Earth, but that's not the only application of hyperspectral remote sensing. Then, so how did you start to work on this particular way of using hyperspectral remote sensing, where you're wanting to work kind of from space and getting this big picture of Earth?
Yeah, many years ago, this technology was very unique, and we had like 3 or 2 sensors worldwide. One of the sensors was in JPL, NASA, and we used the data and we processed the data and we try to figure out what we can actually extract from the data. But this was years ago. And then other private company evolved, and they also produce sensors that we could use. And from time to time, we brought this sensor to Israel, and we covered lots of areas in Israel, agriculture area, mining district area, and so forth. And we got the knowledge little by little. And the idea was that if you have sensor in orbit, this is totally a game changer because you don't have to lean on the aircraft, you don't lean to have funds to bring the sensor, you don't have to own the sensor. There is a sensor in orbit that covers the globe regularly every 14 days or something like that. So this was a big issue, and we started it 20 years ago. We started this direction 20 years ago, but at that time, the space agency were not that mature to understand the technology, and we faced lots of problem in order to convince them to develop a hyperspectral sensor in orbit. But today, like 5, 6 years ago, it is a bloom.
Okay.
It's a big
Okay.
hype when the space agencies realize that this is the technology of the future.
Okay.
And nowadays, most of the big or the non-space agencies already having at least one sensor in orbit, and the idea is to have in the future more sensor in orbit. And also, it's very interesting to mention that private sector
Hmm.
have developed or have understood that this is the future for their business.
Okay.
And there are many private sectors that are developing today hyperspectral sensor to put in orbit
Okay.
instead of leaning on space agencies. And they will sell not only the data, but they will sell also the products.
Okay. Wow. Okay. So it's space agencies, but it's also private sector companies who are working on this and getting the technology up in the orbit. And so you said right now, every 14 days, you can get an entire image of the Earth. Um, that is pretty amazing. So when it comes to this particular project that you're working on, so we've got this great technology, but from my understanding, one of the issues is that um, the sensors themselves, they have a certain sort of lifespan and they can go kind of wonky after a little while. And so we need to make sure that there are methods of monitoring the sensors to make sure they're working. And that involves something called vicarious calibration sites. So what are vicarious calibration sites and why is this an important component?
Well, every sensor has a deterioration in lifetime of the sensor. And if you are on the ground, you can take the sensor and calibrate it in the laboratory. But what we will do if the sensor is in space? How you calibrate the sensor in space? So lifetime is between, let's say, 3 years to 6 years. But it is not the quality of the sensor in the first year and the sixth year is not the same. And you have to somehow maintain the same quality in order to get the same product out of the data.
Hmm.
So there is a way how to do that. One of the way is to look on the moon and calibrate the sensor with the moon. The other way is to put in the satellite a special device that calibrate the sensor on board. But the problem is, even though you calibrate it, do you get still the same data that you get in the first overpass? So for that, you need to cover a place on the Earth that is not changing with space and time, and all the time cover this area and see what are the changes that you observe, understanding that the changes may be for of the sensor and not of the area.
Right.
So this exercise called vicarious calibration. It's not direct calibration; it's vicarious calibration. So for that, you need some areas in the globe that are not changing with space and time, and you need to find them and also to suggest them for the space agencies, and they will need to actually overpass these areas from one year to another, and we can then compare the information and see if really the calibration is taking place, and we have the quality assurance of the data that we can process later with the data of the sensor.
Okay. 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 So these various calibration sites are very, very stable geographic sites. So by measuring them year after year, we kind of have a sense of what to expect. And so it makes it easier to use that as a basis for calibrating these systems and making sure they're working properly. So my understanding, the project that you're really focused on, there are two potential sites in Israel that you think will make very, very good vicarious calibration sites. So what are these sites? Can you talk about
Yes.
that?
Well, I was searching for vicarious calibration site in Israel for many years already. And not only for hyperspectral, for multispectral as well. There is multispectral sensor also in orbit, which has 7, 12 bands. And I found out that southern Israel is very many places southern Israel you can find areas that are stable in space in time. And later on, when this sensor went to orbit, I suggested it to be a calibration site for hyperspectral sensor. The two sites are the Amiaz Playa, which is in the Dead Sea Rift, and the other one is Maktesh Ramon, which is southern of Amiaz Playa in the Negev area. The Amias Playa is very bright and it's very stable over time. We checked it with the satellite and also with ground measurements. And Maktesh Ramon has a unique features, spectral features that are not changing with space and time. These spectral features are very important for hyperspectral because hyperspectral sees the features, not only the colors, they see the features of minerals. And Maktesh Ramon has lots of minerals that are actually in the very close vicinity, and you can calibrate your sensor, or at least see if the sensor is calibrated, if you get the same map that we know from the ground.
Okay.
So these are two sites were suggested to space agencies. And I had, with my activity during the last 4 years, I had a PhD student, Daniela Heller, who checked this hypothesis that these sites will be uh, very well adjusted for hyperspectral sensor. Because in 2 years already, in 3 years maybe, we have hyperspectral sensor in orbit. Before we didn't.
Okay.
So this was a very good step in order to find out if my assumption that these sites are well placed to calibrate the hyperspectral sensor will work. And she just accomplished her PhD and submitted 3 papers
Hmm.
to the international community.
Okay.
And within this international community, there is a new group that called CalValNet. This group is looking for vicarious calibration all over the world.
Okay.
So not only here, because we have in South America, we have in South Africa, we need also to have in the northern hemisphere. So they are actually
So there's a whole community that.
exactly
Okay.
collected. Actually, this moment, they have now a workshop in DLR Munich about this activity. And on Thursday, I will give a talk about Maktesh Ramon and Amias Playa, which I would very much like to introduce the international community. Some of them already know about this area.
Hmm.
They were here and they will be invited to come and see the areas, but some of them are not still aware about this area. And I'm trying to promote these areas for them because I think in the future, what we will have is going to the area and get information all the time from the ground and provide it to those community. So
Okay.
this community
Okay.
will have real data to calibrate, or at least to find out if the sensor is calibrated and can be performed the same data that they were in the beginning of the overpass.
Okay. So you would be taking the information here and feeding it to the international community. How many sites around the world are there currently?
It's a good question. I think something like maybe 10, 12
Okay.
sites like that. I know there is a site in Australia, in South America, also in Turkey, uh, but also in China. And I think finding these sites is a very important important step, because as much as we have more sites, we will be happy to know that the data are well calibrated. If the data are well calibrated, we can then proceed with the data processing and the final products, which are maps,
Okay.
quantitative maps, uh, will be very accurate, and we will pass all quality indicators that we have developed for these missions.
Okay. Okay. So you've identified these vicarious calibration sites in Israel. What are the next steps for them to become official sites recognized by the international community? How long will that take?
I think first of all, they are already recognized.
They are.
I know that they are recognized by NASA.
Okay.
In NASA, they have now new sensor in the space shuttle,
Okay.
and the name is EMIT.
Okay.
And this sensor is one of the best sensors ever, and we are with them, providing them data to calibrate the sensor. And so far, they're already with us,
Okay.
and hopefully they will visit us next year.
Okay.
DLR, the Deutsche Remote Sensing Center, is also aware about this site, and they are also working with us with their new sensor. They have two sensors. Also, we have a collaboration with the ASI, which is the Italian space agency. They have another sensor in orbit.
Okay.
And in the future, ESA, the European Space Agency, they will have also sensor in orbit. The name is CHIME. And we will provide them the information that we already have, and also information that we will measure in the future. So we are trying to track this process for the near, let's say, 10 years, 15 years, and to provide information to those communities. And I hope that we will be able also to deploy some instrument in the area, and with remote control, we will provide information to the space agency. At the moment, we need to go to the area and measure the soil, and measure the rocks, and also the atmosphere. And it's still, it's still complicated, but in the future, this is what we are foreseeing.
Okay. So it's about going there, measuring all of the data, the qualities of the area, and then that will help get it set up so that you'll be able to eventually feed that information back with relation to these hyperspectral remote sensing technologies. I think it's really cool and really exciting. I mean, you've been working on this for much of your career. So how excited are you about being in this position at this point?
First of all, I'm really happy that young students are now entering this discipline,
Mhm.
and I have to catch them because they are very talent, and they do very nice and very important things. All these AI and ChatGPT is now entering to this discipline as well.
Right, right.
But what I really like about this technology is the discipline that I have developed 30 years ago, which called soil spectroscopy.
Okay.
And soil spectroscopy is getting the information of the soil from spectral information without having to go to the laboratory.
Okay.
So you give me the soil, and I'll tell you exactly what we have in the soil in terms of chemical constituents and also physical structure. And this is very cool, because then you can provide information to the agriculture farmers, to the farmers in the agriculture arena, to give them information about the soil, and they don't have to measure the soil. They just have to have an overpass of a sensor that is mounted on drone or on the space shuttle or whatever, and then I will process the data and provide them pixel by pixel what is the soil condition. And
Okay.
this will help them to fertilize the soil or to find problem of the soil and prepare themselves for the next growing season.
Okay. Okay. I think that's an amazing example when you're talking about soil too. Can you talk to me about how this technology and the work that you've done, how has it really reframed your understanding of Earth itself?
Well, I think this technology, as I said before, it's the MRI of the remote sensing at the moment. And we have lots of breakthrough and game changer all the time with the new activity, new findings. Once you have the spectrum, that is everything is there. You just need to mine the information. So we still, I used to say to my students, we know 25 of the applications,
Hmm.
75 of the applications you have in your mind.
Okay.
So you will have them in the future. But when you have the spectrum information, then all information is there. You need only just to mine the information. And for that, you have today lots of tools, statistical, mathematical, and so forth. So I foresee that the area has a very bright future in terms of what is on Earth, not in terms of the technology that already provide the data, but the processing the data will be the, the next
Okay.
future
Okay.
game changer.
Okay. So it's the amount of data that we'll be able to retrieve. So in my mind, I almost picture, there's the physical Earth, there's the blue and green globe that you see, and now there's this sort of immense informational database that we will have. And it's sort of thinking about Earth in that way.
It's true because if you look on the Earth from very far, it's a blue.
Hmm.
It's blue, the blue Earth, the blue ball,
Hmm.
And when you zoom in into this blue Earth, you see that the Earth is not blue. It
Okay.
has also some gray and some red, and even the red has some differences and so forth by the minerals. And of course, this zoom in is very important, and in order to understand the Earth from space, and this is what we do.
Okay. Well, on that note, Professor Ben-Dor, thank you very much for joining me. It's really exciting research that you're working on, and good luck with these vicarious calibration sites.
Thank you very much.
Thank you.